So today I've been given the great honor of introducing our plenary speaker, Professor Assaf Naor from Princeton University. Naor obtained his PhD in 1999 from the Hebrew University in Jerusalem, and where he was advised by Joram Lindenstrauss. After positions at Microsoft Research and the Curran Institute in New York, he moved to Princeton in 2014, where he's currently the Henry Burkhardt Fine Professor. Professor Naor's website lists his research interests as analysis, probability, quantitative geometry, and applications of these subjects to combinatorics, mathematical physics, and theoretical computer science. His many contributions straddle the border between pure and applied mathematics, often in surprising ways. An unifying theme to his work is to bring insights from geometry of Banach spaces to bear on a variety of problems, ranging from approximation algorithms and unique games conjecture to the quantitative theory of metric spaces, about which we'll hear more today. Professor Naor's research has been distinguished with several awards, including the Salem Prize, the Bowker Prize, and the European Mathematical Society Prize. He was made a Fellow of the American Mathematical Society in 2012. Without further ado, let us hear Professor Naor himself speak about metric dimension reduction, a snapshot of the Ribe program.
Thank you very much. Okay, thank you very much for this opportunity. As you can see, the title of my talk has two components. The main component is metric dimension reduction, which is a big area, and I'm going to give you a substantial chunk of it. The subtitle is that this refers to a much, much bigger long-term research program that has been going on for several decades now, and this is where the topic of metric dimension reduction originated. And I'm going to start with that just to put everything in context before we get to more specific results. So what is the Ribe program? We're going to take some time to look into it. As an overarching theme, it's an organizing principle for metric spaces. Now, when I first heard of this as a graduate student, I was intimidated. When I wrote the word intimidating, I'm referring to myself. Because what is the axioms of a metric space? They seem to be very weak. They're just the triangle inequality. And when axioms are weak, there is a huge diversity. And if you're expected to prove a structure theory or some theorem which has a quantifier for every metric space, you have to deal with everything that the weak axioms allow. So it has to apply to, let's say, on the right you see the internet graph. On the left you see an example of another graph. This is protein-protein interactions in yeast. It has to apply to manifolds. It has to apply to various singular objects. I'm limited here, of course, by 2 dimensions, but it has to apply to very high-dimensional objects, even infinite-dimensional objects, various singularities. It has to apply to groups. Here you see a picture of the Cayley graph of the Heisenberg group, which will play an important role underlying some of the results that we get to in the end. This is just a discrete subgroup of the famous Lie group, where you join 2 elements by an edge if their difference in the group is a generator. So these axioms are weak. There are many more things. We as mathematicians maybe are familiar with the pictures that I flashed, but there are various other metrics that arise as solutions of optimization problems that you just know their properties based on various constraints that they satisfy. There are transportation cost metrics. There are various metrics that are really driven by an application that practitioners looked at, and they are not necessarily something that we studied in undergrad. And if we want to organize this world, we have to come to terms with the fact that it's a complicated world, and maybe it's unrealistic to try to prove a structure theory or have some sort of organizing principle. And one of the surprises of the Ribe program is that there is actually a way to think about the general metric space in a more structured way. And that relates to a more tame world, I mean, it's an analogy to the more tame world, to a more tame world, which I will explain, which is normed spaces. Now, normed spaces are in one-to-one correspondence with centrally origin symmetric convex bodies. So, of course, it could be the Euclidean ball, it could be some other convex body. Here are a couple more. The octahedron, the unit ball of L1, will play his fundamental role in a lot of what I'm going to talk about. It occurs in many applications. This is, of course, 3 dimensions. As dimensions go higher, these objects become more and more complicated, of course, but it's more tame. And just very quick reminder, how does this induce a metric? So you were given an origin symmetric convex body, let's say this cube here, you take a vector in Rn, you look at the Euclidean length of the segment joining it to 0, you look at where it intersects the boundary, you look at the Euclidean length of the segment up to the intersection point, and the norm, it's the length of the vector is the ratio of these numbers. And the third line is what's important. This induces a metric, and it's a nicer object. In particular, it's a vector space. It's a and we will see that there is there are a lot of intuitions that come from thinking of from this linear structure. And the correspondence, the last line, is the ball, the unit ball of the norm is just the body. So this is a very quick standard fact about norms. Okay, so I will explain something that started in the 70s. There was a phenomenon that was discovered by Ribe, and we will get to it, which hints but does not give an explicit formulation of a way to think about the crazy objects that you see on the right. Imagine them as though they are normed spaces. So this is an analogy, it's informal. I think what's great about a lot of mathematical programs is there is an informal aspect where we don't really have a clear theorem, but we have this gut feeling or intuition that we develop over time that allow us to think about, let's say, the internet as a norm. And once we translate some question or some concepts into this world, we end up arguing about the objects on the right, making all kinds of arguments, looking for certain phenomena that without this analogy, it would seem completely crazy. So we have like a mental picture of a norm, even though we're dealing, let's say, with the Heisenberg group. Okay, so I want to explain how can something like that come, and it's mysterious. We don't really, this analogy part is under formation still, despite many decades of work by many people. So Martin Ribe, I never met him. He did his PhD in the 70s in Sweden, and then left mathematics. In his short career, he has a few papers, very influential ones. One of them is a rigidity theorem, which is really open Pandora's box. And it's a very influential result, and I want to explain it, but let's start informally. It says that anything you can say about a norm that is isomorphic, finite dimensional, and linear, and I will explain what I mean by that. Any property of a norm which has this finite dimensionality property and allowing errors, constant errors, is actually a metric property in disguise. Now, what do I mean by this? So I need to define the concepts. I need to explain what I mean by an isomorphic finite dimensional property of a linear property of a norm. And instead of just giving a formal definition, I want to give just one of many possible examples that you can keep in mind. So here's an example. It's an important example, but it's not. But this is just for illustration what I mean. So here's a property of a normed space. There exists some constant c, such that whenever you give me n unit vectors, I can somehow come up with a choice of orientation for each of them. So take each one of them, either in the direction it's pointing or the opposite direction. Once I chose this orientation, the length of the sum will be at least some definite lower bound going to infinity. So here I chose cubed root of n. You can imagine other asymptotics. This is not crucial right now. Now, those of you who will look at the proceedings when they are available, you will see that I talk a lot about cotype, or Rademacher cotype, and this is not this notion, but it is related to it by deep work of Talleyrand in the 90s. So, but look, let's look at this condition. So this is isomorphic in the sense that I don't care what the constant is. Okay, so if you change the norm by a constant, the new norm will still have this property. It will just, the little c will change. It's linear because it's a condition involving linear combinations of vectors. And it's finite dimensional because it's about finitely many vectors at a time. Arbitrarily many, but finitely many. It's not about limits of sequences and things of this type. It's statements involving finitely many vectors. So now let's be really more formal. So we have a property P of a normed space. It's said to be an isomorphic finite dimensional linear property. So it's a relative definition. If you give me any other normed space which has the same finite dimensional so Y is the new normed space. If it has the same finite dimensional linear subspaces as X, then Y inherits P. So formally, this new normed space must also have the same property P if you can come up with some constant, let's say 100 million, such that for any finite dimensional subspace f of Y, located anywhere in the space and of any dimension, you can find a companion subspace f prime in X and a linear isomorphism between the two, which preserves distances up to this factor C. C is chosen up front independent of the subspace. So in the previous example, just take the subspace capital F to be the span of the n vectors, the unit vectors for which you wanted to choose the signs. So that's an example. So that's what we mean by a finite dimensional linear property. It's a property of a normed space which is somehow forced by the finite dimensional structures inside it. In Banach space theory, these are called local properties. This is not the standard use of the word local in most of mathematics, but when we say local properties, we mean in this context finite dimensional linear properties, not neighborhoods of points. So Ribe's rigidity theorem says that if you give me any two normed spaces, and you forget that they are normed spaces. Suppose that they are homeomorphic as topological spaces, but not as topological spaces. You want some little bit of quantitative control. So you want the homeomorphism F to be uniformly continuous, and also its inverse to be uniformly continuous. So if there exists such a homeomorphism, then X and Y have the same isomorphic finite dimensional linear properties. Anything you can say about finite dimensional subspaces, no matter how linear it looks, if X has it, Y has it, and vice versa. Just from the fact that they are homeomorphic with uniform continuity. And just a warning that if I replace the quantitative aspect and just allowed continuity, then a deep theorem of Kaditz from the 60s says that then if you think of normed spaces just as topological spaces, then any two separable infinite dimensional Banach spaces are homeomorphic. So this is really about requiring that the homeomorphism to be uniformly continuous. That's an inherent aspect of this theory, that you need quantitative bounds. So the local theory of Banach spaces, which really has its origins in Grothendieck and in Grothendieck's work, where he gave very fundamental definitions and vision and theorems, but the formal notion of the local theory of Banach spaces was due to Robert James. So this is the study of isomorphic finite dimensional linear properties of normed spaces. Because all the norms on our N are equivalent, this is inherently a quantitative theory. This is about bounds and estimates. If all the norms are the same, so you're going to discover differences by measuring things. So there's already 60 years of truly amazing work by many great mathematicians, and this developed to a very, very, very rich theory. So there are structural results, there is a whole range of analytic machinery for vector-valued Fourier analysis, etc., that has been developed to understand this. Invariants were introduced. And this has deep connections to many areas of mathematics in both directions. It uses tools from other areas of mathematics and also has impact on other areas of mathematics. In particular, it had decisive impact on several areas of mathematics. And we actually heard It was behind the scenes in many of the talks that we already heard in the ICM were results in the local theory of Banach spaces. So when you have such a beautiful, rich structure theory of linear objects, and Ribe comes along and tells you that actually all their properties are metric properties in disguise, this is a huge opportunity. So what is the Ribe program? We want to make this abstract notion that isomorphic linear finite dimensional properties of normed spaces are actually metric properties in disguise. We want to make this explicit. So the Ribe theorem suggests that there is some sort of hidden dictionary. There is a way to take anything you can say about a norm, no matter how linear it looks. If it's finite dimensional, you can rewrite it using only distances between points. It doesn't tell you how to do it. It's hidden. There are no entry in the dictionary is written there. But if we succeed to do that, then all of a sudden we can look at the same property, the same phenomenon, the same conjecture for a metric space. And we can maybe do some proof while imagining linear structure in our head, even though there's absolutely no linear structure. So formulated in this way here is what we should do given Ribe's theorem and the suggestions and concrete problems. This was introduced in the mid-'80s by Bourgain. In the decade in between and also before Ribe's work, a lot of the leadership was due to the late Yoram Linestrauss. So this is a rich network of questions. There are many concrete questions about proving estimates, the kind of conjectures that we're used to in mathematics. But a lot of it is amorphous. It's about how to define things. There's a dictionary. We don't know what it is. It's held behind our back. And we're trying to figure out what are entries in this dictionary. So many of these questions and a lot of the things that I'm struggling with is how to even define things. What is the correct definition for certain properties? And so far it had really wide-ranging implications and applications in various areas of mathematics. Okay, so this is the picture. There is this arrow going from the pointy, strange objects that don't look like normed spaces to normed spaces. This is the analogy. This is the hidden dictionary that we do not know. Once we do that, we actually prove theorems about the objects on the right while imagining that they're normed spaces. And there are many theorems that are about metric spaces. The word normed space doesn't appear in them, but the only way we know how to prove them is by having this thought we have a mental picture of a norm, even though there is no norm there, through this analogy. So I want to give one example which is not related to the topic of the talk, just so you see the kind of thing. So here is a situation where we have no normed space. You have a metric space of Alexandrov non-positive curvature. This is just a geodesic metric space, such that whenever you give me a geodesic triangle, and you draw the same triangle in the plane, so I mean the same side lengths, and you interpolate along the edges linearly, whenever you have such a triangle, this mapping from the boundary, which is the linear interpolation, doesn't decrease distances. And if you reverse the inequality, that's non-positive, that's non-negative curvature. So here is a fresh theorem which does not involve the word normed space. It answers a 25-year-old question of Gromov. So there exists a metric space such that you cannot realize it as a subset of any non-positive curve geometry, even allowing for very, very, very weak requirement. You want to assign to every point in the metric space a point you cannot assign to a point in the metric space M, a point in any non-positively curved space, such that in the image, the distances between 2 points is controlled between any 2 functions whatsoever of the distances between the original points. And the only requirement is that the lower bound goes to infinity at infinity. So there is no norm in this theorem. The only way, for 25 years, we didn't know if such a thing exists. The only way we prove it is by doing really Banach space, normed space arguments inside these curved objects via the Ribe program. So this is in the guts of proofs, an analogy, okay? And just so if you reverse the curvature condition, this is simply not true. So there is something very interesting about the implications of the signs of curvature. Okay, so those of you who didn't follow this part, it's not related to the rest of the talk, but I just want to give you the kind of theorems that we can prove where the Ribe program plays a role behind the scenes through this analogy. So now I want to discuss this snapshot, this little corner of the Ribe program called metric dimension reduction. And this is really a little corner of the program. Those of you, there is no book about the Ribe program yet, but there are many very long surveys which are freely available online. Even in the proceedings of the ICM, I broadened the scope and described a lot of it. So if you want to see a lot of context, it's available. But we're going to look at a little corner of this notion. And another caveat that I want to say is that the notion of dimension reduction itself is one of the most commonly used terms in mathematics, in sciences in general. And this is a human endeavor of, I see, like I think every day in the archive, several papers posted which discuss dimension reduction. And that's a much more broad term. It's about, you have some data which looks like it's high dimensional, and you want to come up with some auxiliary latent variables, few of them, so that you can realize this data in low dimensions using this small number of variables while preserving some features that you care about. And as stated like that, it's extremely broad, and I want to, and very, very well studied and very sought after. And I just want to say that I'm focusing in this talk only on the perspective of pure mathematics and only on metric questions, things about preserving distances or distance information. It won't be preservation because we're going to be allowing huge errors like we saw before. So here is the kind of a statement that is true. This is I will get to the actual theorem before. This is just plugging in specific numbers in the theorem. This is a fact. Give me any billion vectors, 10 to the 9 vectors in R billion, so their length 1 billion. If you only care about their pairwise distances up to a factor 2, you can do it in dimension 329. I computed the numbers in the theorem. So you can find vectors of length 329, went down from 1 billion to length 329, and all the pairwise distances are the same up to factor 2. Okay, so this is the Johnson-Linischauss lemma, and we'll get back to it. But and this is the notion of dimension reduction. This is what the term feels like. You have points in high dimension and you want to reduce their dimension. But as mathematicians, we can ask the same question the other way around, and that's how often I like to think about it, is suppose I give you an object which cannot, I want to determine what dimension it can be realized in. Now it's a finite object, living in some continuous ambient space. What do I need to know about this object, these finitely many points? Suppose I know information about their distances up to a factor 1,000,000, or maybe even something weaker. These are only finitely many points lying in a continuous object. There is something about them that forces the ambient dimension to be huge. So if I could understand when I look at a finite metric space that it's actually forcing high dimensionality, even with very crude information, then I will show that you cannot reduce dimension, and of course vice versa. If this obstruction doesn't exist, then you can reduce dimension. So this is really the same question. What forces high dimensionality? Now this is a very interesting question, and we do study it also not in the context of finite dimensional normed spaces, but in this talk I will discuss finite dimensional normed spaces. This is meaningful in many other situations as well. So the first question in this topic that you can ask, it's a problem asked by Johnson and Linischauss in 1984. And, well, it was a question. So they says, can you find a universal constant alpha? Let's say alpha is 10 or 100. Such that give me any metric space of size n, any metric space whatsoever. You can find a dimension which is at most a constant multiple of log the number of points, and a realization and a norm, which you're allowed to cook up the norm to adapt it to the metric space. So you want to realize your endpoints as endpoints in RK, and invent some norm in RK, these few, such that in the image, all the pairwise distances are up to this universal constant, alpha, 100, let's say, the original distances in your abstract geometry. So whenever this final line here holds, I'm going to say this a lot, we say that the metric space embeds into RK with this norm with distortion alpha. So let's say a few words about where is this log coming from. So log n is really the best you can hope for. So this is the most optimistic conjecture. And this is just in essence because this is the amount of information which is contained even in trivial metric spaces. So if you start even with a trivial metric space and the distance between any 2 points is 1, 2 distinct points, then the requirement is to come up with some norm such that in the image the distance between any 2 points is between 1 and alpha, and then this is a very simple picture. You just fix some arbitrary point in your metric space. Let's say this is what the unit ball of the norm looks like. So the whole action happens in a ball of radius alpha, so any other 2 points are inside, that's a requirement. Their distances is at least 1, so if you draw balls of radius a half, they can at most touch in the boundary. Of course, it's not really that the picture is this. There could be a point on the boundary of the ball, so actually everything happens in a ball of radius alpha plus a half. And now you just compare volumes. You look at the union of these balls, and because they're disjoint, the volume adds up. And when you compare the volumes, you see that the dimension has to be at least log. So the most optimistic you can be is that an endpoint metric space is realized in log n dimension. This is a very simple volume consideration. So that's one reason, but there is a bigger reason within the Ribe program. And that's the context in which Johnson and Nishaus discussed this. They were interested within this framework of analogies to prove an analog of a classical theorem of Fritz-John in the local theory of Banach spaces, which would have followed from a positive answer to this question. Now, I want to say that their question was later solved. There was a twist, but solved in a very meaningful and impactful way by Bourgain in a completely different way. But that was their motivation. And more generally, within the Ribe program, and the Ribe program is about finite dimensional normed spaces. So the first thing you can ask for is what is the dimension of a metric space? And there are many, many ways to do this, but we very often care about infinite metric spaces as well. But in the context of finite metric spaces, it's very good practice to start by imagining that the dimension is log the number of points. I warn you that the reality is much more nuanced, and we need to adjust this intuition, etc. But generally, this is like the first attempt when you try to make this analogy. And of course, this is not of course, but this is the theorem that I was hinting when I plugged in specific numbers before. So Johnson and Nishaus proved that the answer to their question is positive if your endpoints happen to be a Euclidean geometry. They're endpoints in a Hilbert space. So if you give me any endpoints in a Hilbert space and any allowable error tolerance alpha that you want, you can find some k which isn't that big. It's at most a constant depending on the error tolerance times log n, such that, and you can find new vectors just in RK, log the number of vectors, such that the distance between any two of the new points in low dimensions, the shorter vectors, is up to your error tolerance alpha, the original distance. So this is called the Johnson-Nishaus lemma. And the slide that I showed before is just amounts to going carefully over their proof and just seeing what numbers it gives. But this is really significant compression of data. From from vectors of a length 1 billion to vectors of length roughly at 300. So this is has numerous applications, both in pure and in applied mathematics. It's actually called the Johnson-Nishaus lemma, not the Johnson-Nishaus theorem, because within their paper, it wasn't the goal of the paper. It was a lemma towards some theorem in pure mathematics. So I just am rewriting here the question, the initial question. Can you give me an endpoint metric space? Can you realize it into some low dimensional, log n dimensional, into some RK when k is of order log n, while preserving distances up to a constant factor? So Bourgain showed that the answer is negative. You cannot do this, but not too bad. Okay, I mean, the lower, but it's mildly worse. So he showed that there is an endpoint metric space such that no matter how you come up with a norm on RK, if your metric space is inside that norm, then K is not log n, it's at least something like log n squared, actually log n over log n squared. So this is a very nice, if you want to teach this theorem, it's a very nice application of the probabilistic method because it's a double application of the probabilistic method. Bourgain used both random graphs and the Johnson-Lillenstrauss lemma itself, which uses a randomized construction, random projections. So it's not long, it's a very nice argument. In essence, it's showing that the fact that you can reduce dimension in a Hilbert space means that there must be some other metric space which doesn't embed into any low-dimensional space. Somehow he flips it on its head. Okay, this lower bound log n squared, log n over log n squared. Okay, it's not the log n that we were hoping for, but it's still great. If we could do this, that would be great. And immediately after proving this theorem, the main question that Bourgain asked, the obvious question is, what is the correct dependence? And maybe even log n to some constant is the truth, and this conjecture was repeated by other mathematicians in the years that came after this. Completely obvious question. And a decade between Bourgain's theorem in '85, a decade later, there was an improvement, but only this log n in the denominator. So Linian, London, and Rabinovich succeeded to lower this bound. They found an endpoint metric space which requires dimension log n squared, not log n over log n squared. So a little bit of improvement. So maybe we're in a good situation. Until 1996, in 1996, Matouche came along, and I really think stunned the community and showed that the answer is awful. So you can come up with an endpoint metric space such that if you want to embed it into RK with any norm whatsoever, these are just endpoints, it forces K to be exponentially worse than the original guess. Some constant power of n. Now, so this is bad news, and we will soon see how we turn it into good news. So this is just a wonderful theorem that I recommend reading. It's a nice combination of combinatorics, functional analysis, and the new input is tools from real algebraic geometry. Matoušek was a huge loss to the mathematics community between the last two ICMs, this one and the previous one. He passed away from a serious illness. He was a massively original mathematician. And this injecting real algebraic geometry into this picture, I don't want to put words into the mouths of Johnson and Bourgain. I was an undergraduate at the time, and I can just tell you that I observed it from the side that they were surprised by this connection. Okay, so I want to turn this bad news into good news, and in order to do that, I want to make this bad news even worse first. So a couple of years ago, I proved the following theorem, which is the same conclusion as Matoušek's theorem, except that this, by Lipschitz, this preserving all the distances requirement is now changed to preserving only the average distance. Okay, so you can find an endpoint metric space such that for every norm whatsoever on RK, if you could realize these as endpoints in RK in such a way that, let's say, distances don't increase, later we'll change this to an average as well. And the only thing it requires is that the average distance is what it should be in the original metric, not all pairs. This forces the ambient dimension to be exponentially worse than you would have guessed. So there is some configuration of points such that if I put them in RK with any norm whatsoever, and I give you very weak information, I tell you what their average distance is up to a factor 100, 1,000,000, that forces the ambient continuous object to be very high dimensional. Okay? So that's worse news. And in order to explain why this is actually can be flipped on its head and used to prove positive results, I want to explain that what is this bad metric space. So unlike Matoušek's theorem, now we have a criterion for high dimensionality. It's not an existential statement using algebraic considerations, it's a criterion. And the bad guys here are expanders, which already appeared many times in this in this conference, both in the plenary talks and in several sections. I heard it mentioned many times. Let me remind you the combinatorial definition. Very quickly, I want to show you something non-standard about them. So an n-vertex graph is an expander, constant expander. If it's constant degree, so every vertex has boundedly many neighbors. And whenever you give me any subset, then and you look how many edges have one endpoint in the subset and one endpoint in the complement, that's at least a constant proportion of the subset, of the size of the subset. So if the subset is, let's say, what's to the left of one of these lines, for every way to cut the graph into two pieces, there will be many edges going across. And what you should imagine is some tangle like this, that even though every vertex has few neighbors, it's just you cannot cut it into two pieces without seeing many, many edges going across. So this is the standard combinatorial definition. We heard it. I want to, and I will discuss these as metric spaces. I'll always take the shortest path metric on these graphs. So when I think of them as metric spaces, think of them always as equipped with the shortest path metric. So now I want to explain to you a reformulation. This is really a reformulation of what it means to be an expander, and I think it maybe highlights some of how non-intuitive this notion is. So here's a puzzle. I'm standing here, I'm looking at you, the audience members, and I'm asking, what is the average Euclidean distance between all of you? Okay, so of course I had no idea what this lecture hall would look like, so I put into Google Images lecture hall in a university, and this came up. I'm way off, it's okay. But that's what I had to work with. So suppose this is what I'm seeing. And I want to know what is the average distance between the people. So I stated this is a puzzle, this is a triviality. What do? I join each of the audience members by a straight line, compute its length, and just take the average of all the numbers that I got. I mean, what's the big deal? Well, okay. How many numbers do? I look at all the audience members, choose two, these are all the pairs, and I take the average of these numbers. So, of course, I didn't have before coming here, I didn't know what this lecture hall would look like. But I did get an email from the organizers with a schematic description of the lecture hall. So it says that it has 5,350 seats. So let's just take the average distance between the seats. Not all the seats are taken. So let's take this number and let's compute. And we see that the number of distances that I'm computing is more than 14 million, roughly 14 million. So if I want to know the average between the distances between the seats in the lecture hall, I take the average of 14 million numbers. Can I do this faster? Suppose I want to know the answer up to a constant factor. The argument I'm going to show below gives easily constant factor 8, but you can actually get it to be 1 plus epsilon. That's not the main point of my talk, but so I want to know the average up to a constant factor. And I'm going to do something, I'm going to propose the following suggestion, which we'll discuss in a second, which is I'm going to impose structure on all of you, even though a priori there is no structure here. So I'm going to choose an expander, any expander, they exist, let's say a random 3 regular graph with 5,350 vertices. So every vertex has 3 neighbors, so the number of edges here is roughly 8,000. And a completely arbitrary bijection between all of you and the vertices of this expander. So I somehow impose structure on you. And my proposition is I'm just going to compute the average of these distances. So 8,000 numbers instead of 14 million numbers. Okay, so if this is the picture, then maybe one person has 3 neighbors. I'm going to compute only these 3 distances, no other distance. These distances for another person, etc. Okay, so this is the scheme that I'm proposing. Here's the important requirement. I'm declaring this recipe up front. I don't want to succeed with high probability. I want to always succeed. I want to be 100% certain that I know the answer. Okay? All of you know the rules, and moreover, I'm making it even harder on myself. I want to know the average distance between the audience members, not right now when you're sitting in this audience room, but wherever you will be tomorrow at 7 p.m. Okay? And you all know the rule. I declared each of you, which are the 3 people from which I'm going to be computing the distances. I declare this up front, and I want to know the average distance tomorrow at 7 p.m. with certainty. Okay, it's easy to sample if you want, but I want with certainty. So we're in Rio de Janeiro, and there are two very fun places to go. It can be Copacabana or Impa. And let's say the top part of the picture decides to go have fun tomorrow at 7 p.m. at Impa, and the bottom part decides to go to have fun in Copacabana. If you do that, then I'll measure, again, the distances between the specific three people that I declare up front, and I will get the right answer. You want to make it harder for me, you can spread yourself over the city anywhere you want. The same recipe will work. You want to go into the water and form this nice picture? I'll apply the same recipe which I declared up front. I will get the right average distance. So a priori, and I actually, when I meet non-mathematicians and I tell them that they can do this, they are surprised. Because it seems that you can foul the plan. I declared it. I'm allowing you to do whatever you want tomorrow at 7 p.m. Surely you can make this plan break. And here's a fact. This is not an if, this is a reformulation. It's an exercise that you can give to a good student. So my recipe will succeed, my goal will work, if and only if the combinatorial definition of expansion held. Okay, so this is simply a reformulation of the same notion, but now it's geometric. That is, if I impose this structure on the audience, my success is equivalent to saying that the structure was an expander. So we saw spectral definitions with combinatorial definitions. You can take this as the definition. How the way this graph interacts with free space. All of us as mathematicians, when we see a statement of this type, there is an obvious thing that you can ask, which is, what was special about Euclidean geometry? And the minute you ask this question, a world of structure and richness opens up. So it turns out that this characterization is a property of Euclidean geometry. And so let's define what it means to be an expander relative to a metric space. So you're given a metric space, and now we have a graph, and we say that the graph is an expander relative to the metric space if no matter which configuration of points indexed by the vertices of the graph you give me, the average distance will be up to a constant factor, the average distance only on edges. The same exercise that I did with Rio de Janeiro, just in some other geometry, a manifold, some other normed space, etc. And more formally, if you don't want a big O of one expander, a constant, you're allowing everything will be quantitative, we'll say it's a C expander if this holds up to factor C. I'm emphasizing the upper bound because it's, again, a nice little exercise for a student to show that the lower bound is automatic. It's really about the upper bound. Okay. So to recap, the classical notion of expander is the same as being an expander relative to a Hilbert space, or R3. Even 0, 1. And this is the fact that you need to be an expander is obvious from the picture that I drew. Because I drew the top part of the audience going to Copacabana and the bottom part going to Impa. If there are not sufficiently many edges to detect this separation, I will never get your average distance right. And this has to work for every partition. So this is completely obvious that you need to be an expander for this to work. But the if and only if is about Euclidean geometry. And in general, the situation is very subtle. We have been working on this very hard for 10 years, mostly with Manor Mendel. There is a lot of information, but there is a lot of great open questions and a really rich structure that emerges. So the kind of things that you can see is that you can come up with very nice metric spaces for which do not admit any expander whatsoever. So this thing, why do expanders exist? That's about Euclidean geometry. So if you think that the existence of expanders is non-intuitive, it's indeed non-intuitive. It's not always true that expanders exist when you change a geometry. You can get nice metric spaces for which, if you choose a uniformly random graph, then with probability tending to 1, it will not be an expander. So this intuition that random is best in combinatorics is false in this situation. Nevertheless, there are specially constructed expanders with respect to these geometries. So they're special, and a uniformly random object will not have this property. There are even what we call super expanders, which are expanders which are simultaneously expanders relative to many very different looking geometries. There are actually two constructions. One of them is due to Van Saun-Laforgue, who will talk tomorrow about something else. And the other one is due to Mendel and myself, and these are very interesting graphs, and they're definitely not easy to come by at this point, at least. So the minute you change the perspective you rewrite the notion of expansion. Instead of combinatorially, geometrically, there is an obvious generalization, and this obvious generalization just opens a completely new perspective on this a very well-studied notion. So the theorem that I really proved is that if you give me any expander in the classical sense, so a combinatorial in the usual counting edges leaving set sense, and you give me any norm on Rk, then this guy will be still an expander relative to the norm on Rk, but the C in the C expansion, the equivalence of the two averages of distances, will be a log the dimension. Okay? And this is sharp, that's not important for us right now. So let's quickly see that just this statement about expanders, geometric expanders, immediately implies this dimension reduction impossibility result for the expander itself. So suppose you assigned to every vertex of the expander a point in some norm, in Rk with some norm. In such a way, this is what I said that before I wrote a Lipschitz condition, now I want the conditions to be an average. I want the average distance along edges to be at most the average distance in the graph, which is of course 1. That's a definition of the shortest path metric. If two u and v are an edge, their distance is 1. And you want the average distance in the image to be at least the average distance in the graph, which is a very simple counting argument because it's 3 regular or constant degree. The answer is log n. So these two averages of distances between vectors in the norm are log n apart. But I also said that such an expander is a C expander when C is log k. So they have to be within a log factor log k of each other. So this log k must compensate for the log n. And that means that the dimension is at least n to some power. So this lowering the dimension comes from actually showing that an expander upgrades to an expander relative to a norm with a very mild loss in the constant. It can be much worse when you leave norms. So that's how you prove, so this is some sort of a positive statement, you're an expander relative to a norm, but it implies that this object can't be low dimensional from this very little computation. So this is it, any embedding of an expander into a low dimensional norm space that preserves the average distance requires cannot be done into dimension n to the low 1. It's at least n to some constant. So this is a very different solution of this problem that we started with of Johnson, Lindenstrauss, and Bourgain. In particular, there is no algebra. This is an analytic solution. And it's now a criterion, expansion. It's not an existential statement. What Matuszek did was he gave a very large family of metric spaces and he showed that for algebraic reasons, they cannot all lie in a low dimensional space. Here we have a criterion. I can give you an object and you can check, is it high dimensional or not? This is going to be important for us in a second, that the distortion is actually low dimensional. You cannot do it while preserving average distance. And this specific question of about embedding expanders into low dimensions was asked by computer scientists that are Antonin Nguyen, Nikolov, Rosenstein, and Weingarten. And they actually expected the opposite, that you could embed expanders into some low-dimensional norm because that would confirm a widespread belief at the time that a certain algorithmic task is impossible to do. Okay, so we have really bad news. You cannot lower the dimension, their conjecture is false. But they ask this conjecture because they believe that some algorithmic task cannot be done. So what happens when you disprove such a belief? Is this bad luck, or maybe we have an opportunity here? Let's revisit what's going on. So wait a minute, if you give me a k-dimensional norm, it does contain many graphs. Trivially, you can, what we call geometric graphs, give me any subset of the norm, and declare two elements in the subset to be neighbors if their distance is at most 1. 1 is any parameter, I just normalized. Now this graph is in the norm, it's drawn inside the normed space. We have to reconcile this with the theorem. And there are only 2 ways to reconcile it with the theorem. Well, one of them is that the dimension is huge. But if the dimension isn't huge, then either the average distance was not large, which is, if you think about it, just means that there must be a small ball that contains many, many points, much more than expected. So this set is clustered. Or this geometric graph is not an expander. Now, what is the definition of an expander? The definition, if you're not an expander, means you can partition it into two pieces with very few edges going across. These edges were designed to measure proximity. So you can cut your set of points into two pieces which are mostly far apart. There may be only few pairs which are close to each other. This is a beginning. Any analyst who ever tried to think in a multi-scale way, this is a beginning of an induction. And indeed, this gives a structure theorem. You give me any normed space, you can do this hierarchically and get a representation of an arbitrary subset of it using a tree structure, so partition, 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 in a way which is dictated by the intrinsic geometry. At each step, you either have a dense ball, and the other set is the complement, so a ball which contains many, many points, and the ball is small, a cluster, or some sort of partition that just comes from the fact that a certain auxiliary graph is not an expander, and you can find this partition by level sets of an eigenfunction by using Chigurh's inequality. And you iterate. Now you repeat this for the two halves, et cetera, and you get some structure theorem. So there is small print, which I will not get into. There are substantial issues that we have to come to make this algorithmic. The graphs I drew are not necessarily bounded degree, et cetera, et cetera. We took the care and we sorted all of this out, and we got this structural fact about general norms. And this can be flipped on its head to show that one of the most basic and most important questions in analysis of high-dimensional data, which I, and I think many others, did not believe was doable, is actually has a good solution. Due to the fact that the lack of low-dimensional embeddings impose structure on norms using this iteration. So I want to explain what a data structure is. So there is a nearest neighbor data structure. So suppose you have a pile of books, and I told you a perfectly legitimate way to store them is the way you see in the picture here. Just put a pile. When your friend comes into the room and looks for a book that has certain specifications, they can go one by one and just find the book that matches their interests. Perfectly legitimate way to store books. We all know, we as human beings, for a long time knew that it pays off to actually work hard and build libraries or indexing systems in anticipation of future tasks. So this could be in antiquity, like the Great Library of Alexandria, or more modern examples like this one here in Seattle. And when you look inside, you don't see a pile of books, you see order, and you can find books much quicker because you worked hard in preparation of the future query. So as an example, this is the library in Stuttgart, or this marvelous 19th century example here in Rio, which I recommend that all of you see if you have time. So we do this. We human beings organize data in anticipation of future tasks. This happens, and we are very much interested in this. So the approximate nearest neighbor search problem is the same thing, but now your books are points in our K. So it's n points. Suppose you have some data set D, it's huge, of n points in our K. So this is just, each one is a vector of length K, so this is K times n numbers. That's all you have, okay? And now at some point a new point comes along. RK is some with arbitrary norm. And you ask, what is the approximately closest point in your data set? Now, for Euclidean norm, I will mention in a second, this was solved, but there are many norms, concrete norms, for which already it was asked and it was not known whether you can build a clever library. So what do I mean by a clever library? If you store your points like an array of Kn numbers, like a pile of books, then you can do this in time. And time for me is the number of distance computations. Let's just put aside issues. All of this is sorted out, but think of how many distances. So a new point comes along, compute the distance to each one of the endpoints. So the benchmark here, can we cleverly construct a library so that we can get an approximate answer, not maybe the nearest point, but something which is approximately the nearest point, in sublinear time, more than just going through the pile of books. So a few days ago, there was a talk of Piotr Indyk in the computer science session exactly on this topic. This is a very well-studied and important question about data analysis. So retrieving data from, retrieving similar points from huge piles of data. So as I said, n is immediate, and there is a perception, a term called curse of dimensionality, and maybe many of you heard about, which is this belief that as the dimension goes, things deteriorate exponentially with the dimension. And the fact that you can solve this problem exponentially is the usual kind of hierarchical partition that we do in RA. You can, in RK, you can just enclose everything in some square, subdivide the square into 4 pieces, and remember which of the pieces contains data points, iterate, etc. And what you see here is a tree structure, which is a better organization of the points. You have to work to make this work. But this is exponential in K because, of course, every square has 4 subsquares in the plane, but when in R3 it's going to be 8 square, etc. And in 8 squares, and a cube of side length 1 will require 2 to the K in the next partition. So even when you go in, if you build a library in this way, even in R3, when you enter your library, you're going to see something like the interior of the Menger sponge. Okay, so this is the curse of dimensionality if you approach this naively. Now, so the benchmark, and it was 20 years ago, Indik and Motwani and Kushilevitz, Ostrovsky and Rabani, they showed how you can build a data structure which is not much bigger. So initially you had k endpoints, now you kn to some constant. And now in time, which is sublinear, goes faster than looking up, measuring all the distance, you can output a data point which isn't the nearest one, it's near up to a factor power of the dimension. But everything is polynomial in K here. There is no exponential decay with dimension. So they solved this actually in the Euclidean case where they got the error was 1 plus epsilon. And this was one of the applications of the Johnson-Lindeshaus lemma, one of many. So, and then you can pass to a general norm using this classical John theorem that I mentioned earlier. And that was the best thing that we could do. So using this structure theorem, which came from dimension reduction impossibility, so we joined forces, the computer science team and myself, and now what we can do is we can give me any library of endpoints in any norm whatsoever. You can store them, you can work to store them in a clever way so that you don't store k n numbers, but in terms of n, it's n to the 1 plus epsilon. Epsilon is arbitrarily small. And when a new point comes along, you answer in time n to the epsilon, not n. An arbitrarily small power of n, you find the nearest point in your data set up to a factor k of delta. I'm being very unfair to the theorem. Our delta actually goes to 0 quickly. Okay, but you can get the arbitrarily small power of k for now. But if you read the theorem, you're going to see that actually this delta goes to 0. Okay, so now with this generality, with the quantifier every norm whatsoever, I did not believe was possible. I don't think anybody believed. And it came from the impossibility result of dimension reduction. There were specific norms for which we did not know how to do this and people cared about, like Schatten-1, the nuclear norm, etc. Where if you just analyze the proof in this case, it gives the approximation is actually a constant even. So there were specific norms that even though this theorem has the quantifier every norm, there are concrete explicit norms for which we did not know it before the theorem for an arbitrary norm was proved. And this came from this dimension reduction impossibility result. Okay, so I have 3 minutes, and I want to just step back a little bit. And this was just one example where I took a metric space and I wanted to embed it into an arbitrary low-dimensional norm. And we already saw in Johnson-Lindeshaus theorem that if your initial metric space was Euclidean, then you could do it. So more generally, if you give me a normed space, let's say some LP space or some matrix space, etc., we'll say that it admits dimension reduction, metric dimension reduction, if for any endpoint in the space, a priori in their span, in an n-dimensional subspace, you could actually find a subspace of your geometry, your space, of dimension much, much smaller, n to the little o of 1, and an embedding of, and a realization of these points in this low-dimensional subspace. So let's say that a norm admits dimension reduction if this is possible. The theorem of Johnson-Lindeshaus, even without n to the little of 1, with a log n, is the same as saying as L2, Hilbert space, admits metric dimension reduction. This is just a rephrasing. We're just playing with words here. It's the same theorem. The theorem of Matuszek, that there exists bad metric spaces which don't amend to any low-dimensional norm, because L infinity is universal, is the same as saying that L infinity does not admit metric dimension reduction. You think I'm using the terminology. Bill Johnson and I, 8 years ago, showed that there exist Banach spaces that do admit metric dimension reduction, but they're not isomorphic to Hilbert spaces. So there are interesting examples. It's not just about Euclidean geometry that you can do this. And for many, many years, it was open whether L1 is especially important in applications to computer science. Lowering the dimension is a very fundamental question. It was open whether L1 admits metric dimension reduction, and this was solved by Brickman and Charikar in a very famous paper, and it showed that L1 does not. And there is a paper that's about to be posted in the archive of myself with Robert Young, which gives a conceptually different counterexample in L1, which has a variety of other applications, and that is where the Heisenberg group comes in. But I will not get into it here. Okay, so here we know in L2, we know L infinity. L2 was done using random projections. L infinity, Matuszek proved this using real algebraic geometry. The L1 proof has various applications, various proofs, all of them involving interesting ideas from mathematics. Nothing else is known. So when P is not 1, 2, or infinity, let alone other spaces that we care about, we do not have either a positive result or a negative result. We simply do not know if these spaces, if you can reduce dimension or you can't. Even in L1, which is especially important, the bounds that we have a lower bound, but we don't have an upper bound, which is even close to it. So positive result in L1 is wide open. And this was just about normed spaces. You can look at, let's say, spaces of measures over finite objects, let's say your computer screen, like spaces of images, and then lowering dimension amounts to representing them using a small number of pixels. And there are various questions about manifolds. You look left and right, there are fundamental open questions we simply do not know. And so far, any progress here involved interesting connections to other areas of mathematics, like, be it real algebraic geometry or expanders, etc. So this is an area which had already interesting achievements, but is really, really waiting for new ideas. And this is something that many people are looking at, and has many applications. So I believe that any new idea will have a lot of impact. So this is just an invitation to look into these fundamental questions. Let's stop here.
So thank you very much, Assaf, for this very nice lecture. As been said many times in this conference, we don't really have the appropriate setup for questions, so I guess we'll just thank our speaker again.